Hello everyone, my name is Michael Petz and welcome to today's video. This will be a presentation for the U of A Math Study Skills class. We're going to be diving into one of the most legendary formulas in all of mathematics, the Pythagorean theorem. In this presentation we will cover the history of the theorem and how it got its name, what it is, how it works, and how it is applied in the real life. Before we get into the math, let's rewind way back to ancient Greece. The theorem is named after Pythagoras, a Greek philosopher and mathematician who lived around 570 to 495 BCE. He founded a school where math and philosophy were deeply connected. It is unknown and often debated how much Pythagoras contributed to the theorem itself, as there is evidence of its use by the Babylonians well before Pythagoras' time. What Pythagoras likely did prove was the theorem systematically, and that's why his name stuck. He and his followers, the Pythagoreans, were kind of like a math cult. They believed that numbers were sacred. In addition to his contributions to the Pythagorean theorem, he also is attributed to the theory of proportions, the sphericity of the Earth, and the identification of Venus as the morning and evening star. So what is the Pythagorean theorem? The Pythagorean theorem applies only to right-angled triangles, those with a perfect 90-degree angle. The theorem is a squared plus b squared is equal to c squared, with a and b being the legs of the triangle, as you can see in this illustration, and c being the hypothesis. That is the side opposite to the right angle, and it is always the longest. This equation tells us that the squares of the hypotenuse is equal to the sum of the squares of the other two sides. In layman's terms, the theorem allows for the calculation of the length of any side of a triangle so long as it is a right angle and you have at least two of the side lengths. Let's talk about why this works. Picture a right triangle. Now draw a square on each of its sides, as is in the illustration. The area of the two smaller squares, those on the side of A and B, when added together, are equal to the area of the large square on the side C. This is the heart of the theorem. It's all about comparing areas. Over 300 different proofs of this theorem exist, some geometric, others algebraic, and even President James Garfield came up with his own. As you can see, the relationship relies upon the fact that the square of a side is equal to its area as far as squares are concerned, and square being when you take one length and multiply it by the other, you get the area. So when you take that relationship and you use the square root function, you can reverse that to get the length. So let's talk about the real life application of the Pythagorean theorem. So I am a civil engineer, and the Pythagorean theorem is used all the time in physics and mathematics. So without really going into what a vector is, just know that it is something that has direction and magnitude. And when you are on a 2-dimension or a 3-dimensional x coordinate, x, y, and z coordinate space, Pythagorean's theorem is used to describe that vector in terms of its x and y components. And as you saw in the previous slide, when you have those two x and y components, they can be used to build the actual vector with its magnitude. In addition to all that you use Pythagoras' theorem for in vector calculations, it is also used in the trigonometric identities. That would be sine, cosine, and tangent. You probably covered these in middle school or so. It basically expands the theorem so that whenever you have a right triangle, you are able to use the angles in substitution for one of the sides. So in that case, you would only need one side and one angle to be able to determine all the other sides and angles of the triangle. As you can see here, this is one of the identities. Sine of theta is equal to O of h, which means the opposite over the hypotenuse. That is used all the time in construction. Finding slope, it's imperative for surveying. Everything that deals with the surveying of land uses trigonometric identities. And a bit of a more complicated example would be Moore's circle. So Moore's circle is used in soil and materials like steel and concrete to be able to describe the principal stresses, which are these points at the very edge of the circle. That would be lambda b and lambda a. Those are the principal stresses. And the way that this works is that when you do a test and you find the stress, the non-principal stresses at a point, you can use those to determine where this C is, basically by adding them together and then dividing in half. That gives you the location of C. So that's where you start your circle at. And then to determine your R value, it's the exact same as it was previously. As you saw before, it would be the one of the non-principal stresses minus the other non-principal stress over 2 squared, and then the square root of that would give you the radius. And with the radius, you are able to determine both the principal stress at the 2 edges as well as the maximum moment for any potential material that you have the non-principal stresses for. So it's very useful for construction engineers like myself when you're designing buildings, because when you do these tests, there's a certain that you can, these samples will have an imparted torsional force into them, and by doing this, you can undo that and find out what the maximum stresses are and the maximum moments are without actually subjecting the material to those measurements. It's also frequently used in soil mechanics. It's a similar idea, but more so looking at different stresses at different depths, because the deeper you are in a soil, the more stress there's going to be on it. And so you use Moore's circle, which is really just a complicated version of the Pythagorean theorem to solve that. That's about all I had. That is the Pythagorean theorem. It's a mix of history, geometry, and practicality.